Hi everyone, welcome back. It's a pleasure to introduce Julio Sampietro from the Universidad Nacional Autónoma de Mexico. He'll talk to us about the homotopy theory of directed graphs. Julio, take it away.
Hello, can everybody hear me? Okay, so I'm gonna share my screen on my computer and I'm gonna show my face on my phone so we can all see each other. So this poster is meant to be an introduction to a joint work with Carlos Segovia, who's gonna also speak in the MCA, that deals with the homotopy theory of directed graphs. So first off, in the classical algebraic topology point of view from homotopy of digraphs, everything is well understood. For example, if you have a simple graph, then you can always contract a maximal subtree. So let's say we're gonna contract this edge, this edge, this edge, and these other edges. So I'm gonna mark a maximal subtree, and then you can always contract it to get basically a wedge of circles. So we contract the maximal subtree, and we get 1, 2 circles. So we get a wedge of circles. So from the classical point of view, graphs are not very interesting. They are rather well understood. So this is why we are looking for other types of invariants that are more combinatorial in nature that can capture the essence of homotopy theory. So most recently, this was done by Grigoryan, Muranov, and Yao. And it's basically the approach that we're gonna follow throughout this poster. So the program led by them has been very successful. Many results, such as the Van Kampen theorem, but also homology, cohomology theories, the Kunet formula have been developed. So there is almost a dictionary between a classical algebraic topology and homotopy theory of directed graphs. So the whole point of our joint work is to try to answer the question if there is a model structure that is compatible with the approach of Grigoryan, Muranov, and Yao in the category of directed graphs. So first of all, we have to be clear on what we mean by a directed graph. A directed graph, or a digraph for short, consists of a set V of vertices and a set relation E on the set of vertices, such that V and V comma V is not an element of the relation for all V in V. So in our context, we deal with directed graphs that don't have multiple edges. So we don't allow, since it's a binary relation, we don't allow multiple edges. So we can have at most one edge that goes from one direction to the other and one edge that goes back. But we can't have multiple edges going in one direction to the other. And we also don't allow loops. So this is forbidden, and this is forbidden. So this is what we mean by a directed graph, or a digraph for short. And what do we mean by a digraph for short? So we're gonna, every time that we have an arrow, we're gonna denote it by X to Y for short, as a way of saying X comma Y is in E, I'm sorry. So what do we mean by a map of digraphs? By a map of digraphs, we mean a map F that goes from the vertices of a digraph G to the vertices of a digraph H, such that every time we have an arrow, X, Y, we have that either F of X equals F of Y, or there is an arrow from F of X to F of Y. Note that this definition allows the contraction of edges. We can collapse edges to vertices, which is not something you can do in the context of, say, quivers, for example, where you can't contract edges. So this is what we mean by a map of digraphs. We also need to make clear what kind of product we're going to use. So we would like to mimic the constructions of algebraic topology. So we need a line element, which is going to be given by the line digraphs, and we need a sort of product. So the product we're gonna work with is called the box product of digraphs. If G and H are two digraphs, their Cartesian product or box product has as vertices the underlying product, Vg times Vh, and we have an arrow if and only if either we have an arrow in the first coordinate and the second coordinate is equal, or we have an arrow in the second coordinate and the first coordinate is equal. So here I drew an example of a box product. Here you have two digraphs, and basically a box product looks very much like the classical product in topology. I hope you can see why, but here is an example of the box product. We also need a line element, but since we want the homotopy relation to be transitive, reflexive, and others, we can't just take a simple segment as a line element. We need to consider line digraphs. So a line digraph is just a digraph that has as vertices the set 0 to n and has exactly one of the edges I to I plus 1 or I plus 1 to I. So basically, a line digraph is simply a zigzag. So for example, this is a line digraph with 4 vertices. And now we can finally establish the definition of homotopy of digraphs, and two digraph maps, Fg from G to H, are called homotopic if there exists a line digraph and a digraph map H that goes from G and the box product of In to H, such that restricted to the 0th phase is equal to F, and restricted to the nth phase is equal to G. A map is called a homotopy equivalence if there exists a map such that they are homotopy inverses. So the compositions are homotopic to the respective identities. So now I'm going to give a quick review of model categories. Model category, a model structure on a category consists of 3 classes of maps: W called weak equivalences, F called fibrations, and C called cofibrations. Every time we have an element that is a fibration and a weak equivalence, we will call it a trivial fibration. And every time we have a map that is a cofibration and a weak equivalence, we will call it a trivial cofibration. And all these different classes of maps have to satisfy the following axioms. First, they all have to be closed under retracts. So retracts in the category of arrows. And the weak equivalences have to satisfy the 2 out of 3 properties. If F, G, and G in the set F, G, and G composed with F, 2 of the 3 maps are weak equivalences, so is the third. The lifting axiom that states that in this commutative diagram, if either I is a trivial cofibration and B is a fibration, or B is a trivial fibration and I is a fibration, there exists an H that fills the diagram. So a solution to this problem. And finally, the factorization axiom, which says that every map can be factored as a fibration followed cofibration followed by a trivial fibration and vice versa. So the model structure we are proposing is one that follows closely the approach in classical homotopy theory, where the fibrations are maps that satisfy the homotopy lifting property for any space. So if for anyone familiar with classical algebraic topology, this is very similar to a Hurewicz fibration. So basically, every time we have a lift of a map, we can always lift a homotopy, as in the following diagram. We also need the concept of weak equivalences, and the concept of weak equivalences comes from the concept of weak homotopies. And 2 digraph maps are weakly homotopic if for every finite digraph map, H from K to G, the compositions are homotopic. So it's basically being homotopic, but only on some finite subsets. We say a map is a weak equivalence if there exists a weak inverse. So there exists a map G from H to G such that the compositions are weakly homotopic to the identities. And finally, we define a cofibration to be precisely a map that satisfies the lifting problem with respect to a trivial cofibration. So a map I is going to be a cofibration if for every trivial fibration, it satisfies this diagram. In particular, one can show that the trivial cofibrations are just inclusions of induced subdigraphs. So an induced subdigraph just consists of a subdigraph, so a subset of the vertices, such that every time there is an arrow in the big digraph in G, there is also an arrow in the small digraph. So basically we include all the vertices and all the arrows. And I think that's about the time I have. So just a few last finishing comments. So here we follow the approach that Grigor, Jan Muranov, and Yao used, which is the box product of digraphs. But there exist many different products in the category of digraphs, and they are all interesting in their own right. So we can always look for other product structures, and we'll get different homotopy theories. It's also a bit similar to the category of small categories, but nevertheless, when we try to develop the model structure inspired by the model structure on the category of small categories, everything broke down because we need a composition law, and this composition law eventually gave rise to pentagonal relations that simply are not compatible with the homotopy theory we're looking for. And finally, Grigor, Jan Muranov, and Yao also developed a homology theory and cohomology theory of digraphs. So another interesting question would be to know if there exists a Quillen adjunction between the model structure and the model structure of chain complexes that could come from the homology of digraphs. So I think this is everything I have time to say.
All right, let's thank you, Julio, for a nice talk. Dorit, you'll have to teach me how to ask people to unmute because I found that was cool. Let me ask later, of course. Let me ask if you have any questions.
Maybe I will have one.
Yes, okay, Andrew.
Yes. That's very interesting. I would like to know what happened if instead of these notions of graph, you use, let's say, one truncated Saint-Picel set. In other words, so-called reflexive graph, things of the sort. And also, maybe you use the Cartesian product. It's just very naive questions. I mean, why is it that people are choosing this very restrictive notions of graph, which is nice too, but why should they be simple graph, for example, not multi with a lot of arrows, things of this sort?
Yes, so that's a very good question. I think the main reason why, at least I'm gonna try to partially answer it. So the reason why Grigor, Jan Muranov, and Yao developed the theory first for this kind of simple digraphs is that they first developed a homology theory. And they developed a homology theory for something called path complexes. And this is the most simple setting they could find, and this is the setting that they developed it. But they also have developed the notion of quiver homotopy. And we can work with, Carlos and I worked with a notion of homotopy that allows for loops and multiple edges. But what we found out is that if you allow multiple loops, if you allow loops and multiple edges, essentially every digraph is also homotopy equivalent to a simple digraph. So in this context, we can always restrict our attention to simple digraphs and everything will be the same up to homotopy. So this is why we are working with simple digraphs. I hope this answers your question.
Thank you. That's, thank you.
All right. So we